Okay, we're going to get right to work here because we have a lot to do. So the exam, we were supposed to have an exam when? Was it supposed to be Thursday? Or Tuesday of next week? And then a final the next day? And so what I'm proposing to you is that we change that. What do y'all think? Where we just have a final? And then what would it, because we're really not going to have a whole lot more material. So we just have a final, and then what I'll do is make it where we'll count your highest test grade double, okay? And we'll just equally weight all the exams. Does that sound like, we'll work something that's the best for everybody. Does that make sense? All right. But just for now, let's just not plan on having a test on Tuesday. We're just going to have a final next Thursday, and that'll be it. Okay? All right, so we ended last class. We were, I'd introduced you to the ratio test, and we had started this problem, and I asked you to go and see about getting that. Anybody able to finish this off? No? Okay. We had, at the end of this, when we set up the ratio test, this limit that we had to figure out what was happening. And so when we went through, we realized that we were going to have to turn this from something that looked like 1 to the infinity into infinity times 0, and then have to drop this n down as a 1 over n. That way we could get something that looks like 0 over 0, and then apply L'Hopital's rule. So I'm just going to finish this off. All right, so we have natural, actually I'm ready to do it on today's notes. Okay, so we have natural log y equals, by L'Hopital's rule, limit as n goes to infinity. And now we have to take derivative of the top and the bottom. So what is the derivative of this? And you could split this into 2 logs if you want before you take a derivative. What would you like to do? Split it or just keep it? Just keep it? Okay, we'll just keep it. Derivative of natural log of something is 1 over whatever's in there first. So what's 1 over this? Just flipped over, right? So it's n plus 1 over n times the derivative of what's in here now. So you would have to do quotient rule on that. So I'll do a quick quotient rule next to this. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And then on the bottom, the derivative of 1 over n is negative 1 over n squared. All right, now this looks kind of bad, but I think it cleans up a little bit. One of the n plus 1 factors cancels right here. And then what's this numerator turn out to be? What is this? Just careful. Yeah, this is n, this is just n plus 1 and then minus n. So just 1. Go with me? So we had a 1 over n. Now we're going to have another 1 over n. And then over negative 1 over n squared. And I think when you flip things around, that's just negative 1. Clean it up, cancel n's out, you get negative 1. So natural log of y equals negative 1. And then remember that at the end of the day, we wanted to know what y was. Uh-oh. Someone had a good weekend? Yeah, looks like it. At the end, we want to know what y was, so we have to take e on both sides, right? Take the exponential, apply it to both sides. That'll give us y equals e to the negative 1, which is the same as 1 over e. So, what does that mean? We get 1 over e. Going back to last class, we were applying the ratio test. This limit turns out to turn into 1 over e. And the ratio test says what about that limit? What is our conclusion? What can we draw as a conclusion? Absolutely converges. So ratio test says that if this L, which is our limit, is less than 1, 1 over e is less than 1, therefore, the original series converges absolutely. And of course, absolute convergence implies convergence. So that series converges. All right. Now, we're going to move on to the next test. Unless you want to see another ratio test. Well, we're going to see a lot of ratio tests the rest of the day, so I think we can put it to rest right now. The root test is next. And of course, the root test is here for you. It says if you have a series, if the limit as n goes to infinity of the square root, or sorry, not square root, the nth root of the absolute value of a sub n equals L, and it says there, or infinity, then what's the conclusion? L less than 1 means what? Convergence. And L greater than 1 or infinity is divergence. And I just want to make sure that you're clear. Remember on the comparison test. If you look at that, part 3, we did the comparison A sub n over B sub n. Remember that? It said that if that was equal to C, that C that we got had to be finite. I think I told you to add it in here, right? It said C must be finite. If it was infinite, then the test actually failed. But with the root test, it's okay if this limit is infinity. That will tell us divergence. All right. So let's see this one in action. Oh, and what is the limit saying? It's saying what we're going to do is we're going to take the whatever is inside our series, right? The sequence definition. We're going to take the absolute value of it, and we're going to take the nth root of it, figure out what that limit is. What do the notes say on the side here? What is this good for? Useful if a sub n involves nth powers, right? Nth powers. So here's an example of one. The thing about root tests, they're usually very obvious as far as when to use them. Let's say we have sum n equals 1 to infinity, 5n plus 1 over 11n minus 1 to the nth power. So if I were doing this problem, I realized I could do the nth term test. I'd go through all these, right, and try and figure out what it fits into. But the thing that I'm really focusing my attention on is the fact that the entire expression is raised to the nth power. And the root test says the first thing I'm going to do is I'm going to take the nth root. And so the nth root of something to the nth power is just going to wipe each other out, right? And so all you're really going to be focusing on is what's in here. So that's why I'm leaning towards the root test right now. It's not geometric, right? This is not a geometric series. We said that if we saw n as a power, we'd be thinking geometric. The problem is the base here is not a constant. It depends on n also. So I kind of rule out geometric because of that. All right, so root test. Take the limit, n goes to infinity, of the nth root of 5n plus 1 over 11n minus 1 to the nth power. It says to take the absolute value, doesn't it? But I don't need to take the absolute value here because it's already a positive term, right? 5n plus 1 over 11n minus 1 will always be a positive number. So this is just limit n goes to infinity of 5n plus 1 over 11n minus 1. And if you do let n go to infinity here, you get infinity over infinity. You can use L'Hopital's rule one time, and your answer is 5/11. And that is less than 1. Therefore, the original series converges. No idea what it converges to, but it converges. All right, with that, off of page 463, 3 through 11 odds just show convergence. Then 19 through 39 odds. Just double check that, 463. All right, there's something here in this section that I'm skipping over, but I want to make you aware of it because it may pop its head up somewhere else in another class. So I just want you to know it's in here. I won't test you on it. It's on page 457. It's called the alternating series estimation theorem. And here's what it says. I can let you read through it yourself. There's a little explanation about how they get it above it a little bit. But let's just get down to what it says. It says if we're calling S some sum, all right, so we have an alternating series. That's what we called capital S, okay? So we said the sum of a series we call capital S. So let's say we're trying to figure out what that is, right? All we've been able to show is it converges or diverges a lot of the times, right? Unless it was geometric. But this is an alternating series. So if you have an alternating series, we have a way of estimating what it adds up to be. But again, it's an estimation. It's not the exact sum. So if this, and we have a couple of other conditions. First of all, 0 is less than or equal to b sub n plus 1, which is less than or equal to b sub n. And the second condition, the limit as n goes to infinity of b sub n equals 0. So what does this mean? What does part 1 mean? What does this inequality mean? It's decreasing, right? But not the alternating part, right? Just the part that's not alternating. If that by itself is a decreasing sequence of numbers, and it goes to 0, right? The limit of those goes to 0. Then here's a conclusion. What we call capital R sub n equals S minus S sub n is less than or equal to B sub n plus 1. All right, let's try and figure out what this is saying. All right, it's a theorem, which means this has been proven to be true. Right, we're not going to go through the proof. Capital S is what we want, right? That's what we're trying to figure out. Capital S. What is S sub n? What's that? S sub n? Anyone? Everyone's so quiet. Come on. No? S sub n? What's the difference between capital S and S sub n? We should just take a quiz, one sheet of paper. What's S sub n? No? No one? Well, it's a sequence, but how is S, capital S, different than S sub n? What's that? Yeah, it's only out to n, right? Look, if you remember when we were doing telescopic, right? Telescopic series, the collapsing series, what you did is you found a pattern where things canceled, then you wrote out what S sub n was. That took you out to the nth term, and then you found the cancellation, then you let n go to infinity. S sub n is the nth partial sum. It's the sum only out to the nth term. So what this theorem is saying is as long as our alternating series follows these conditions, then the difference between the true sum and the nth partial sum, okay? That means our error, right? How much we're off by. If we only sum out to, let's say, the first 100, the difference between that and the true answer will always be less than what? B sub n plus 1. That means just go out here to the last one, right? To the end, go one more than that. Whatever that number is, you're guaranteed you're off by that much. I'll give you an example. I wasn't going to, but I'll give you an example. Here's an example. Let's say we have n equals 0 to infinity, negative 1 to the n over n factorial. This is an alternating series, right? My question here is, find an estimate, all right? Estimate correct to 3 decimals. So I want you to tell me what that adds up to be, and I want you to be correct within 3 decimal places. So that's, what, tenths, hundredths, thousandths? I want you to be within 1/1000th of the correct answer. Well, we have to first realize it's an alternating series, right? So it does fall into this category right here. What would B sub n be for us? The part that's not the alternating part. 1 over n factorial. Okay, so then you ask yourself, is this decreasing? Is B sub n plus 1 smaller than B sub n? And I won't go through the work, but you'd plug n plus 1 in here, right? You plug in, well, just leave n in there and then compare them. That inequality would be true. All right, so we won't go through that. We'll just say, yes, that's true. The second thing is you need the limit as n goes to infinity of B sub n, which is 1 over n factorial. You need that to be 0. That's the other condition that we need for this theorem. Is that true? Then goes to infinity here. That goes to 0. So that's true. The conclusion then, all right, our conclusion is that the true sum, the difference between the true sum and S sub n is less than B sub n plus 1. What is b sub n plus 1, by the way? 1 over n plus 1 factorial. So I want to be off by no more than 3 decimal places, so 1/1000. So let me plug in a value of n here, all right? Let me plug a value of n in. N, let's say, is equal to 2. Then what I would have is that my sum minus the second partial sum is less than 1 over, plugging in 2 over there, we get what? 3 factorial? 3 factorial is 6. So the difference between my error here is 1/6, right? 1/6. What if n was 3? It would be what? 1 over 4 factorial, which is 24. 1/24. So as decimals, let's just get your calculator out. What's 1/6 as a decimal? I mean, we'll have to approximate it. It's 1 divided by 6, then 1 divided by 24. What do we have? Okay, 0.1666. And then over here, what's this one? 0.0416. What I want to do is I want to go far enough out with n so that the tenths, hundredths, and thousandths positions of these two are the same, right? So that my error is smaller than 1/1000. So let's go out to something bigger. How about, let's go somewhere where I know we'll be probably safe. How about n is 6? Try 6. You get s minus s sub 6 is less than 1 over, what, 7 factorial, because it's n plus 1. You have to do 7 factorial, 1 divided by that. Who's got that? Sorry, so go ahead. What is it? E to the neg, so 198, is that what you had? All right. Let's go, it looks like tenths, hundredths, thousandths, we have 0, 0, 0, right? Tenths, hundredths, thousandths. Let's just go n equals 7 just to confirm. S 7 less than 1 over 8 factorial. And what is 1 over 8 factorial? It's smaller than that number, right? (248). See? So look, the difference between these two, tenths, hundredths, thousandths positions, those don't change as you go from one to the other, correct? So that means that if n is 7, if I keep going, n is 8, n is 9, n is 10, it's not going to get any more accurate in terms of the first 3 decimals. It's going to stay the same accuracy, isn't it? My error is only going to be off by smaller than 1/1000. So how can I approximate the sum then? I mean, if I'm telling you n is 7 is good enough, can I just now find the 7th partial sum? I mean, just take the sum, n equals 1, and stop at 7 of -1 to the n over n factorial, which would be, let's write out the terms. If n is 1, we get -1 over, oh wait, did I start at 0? Yes, okay, start at 0, apologize. So what's the first term? Plug in 0. Should, -1 to the 0 should be 1. 0 factorial is 1. Then plus, now plug in 1, you get -1 over 1 factorial, which is 1. And then plus, plug in 2, 1 over 2 factorial is 2. plus negative 1 over 3 factorial, which is 6, right? 4, which would be 1 over 4 factorial is 24, and then plus negative 1 over 120. So where am I? N equals 0, 1, 2, 3, 4, 5, 2 more, right? 2 more. So plus 1 over 720, and then 1 more, negative 1 over 5040. That's it. Whatever, now I'm not going to add it up, but whatever that adds up to be is the approximation of that sum correct to 3 decimal places. Now, the great thing about this theorem is that if you're actually using an alternating series, or you need to find the sum of an alternating series, and you're, again, building something and you have certain tolerances, you need to be within, 1/100th of an inch tolerance, then you only have to go out a certain amount before you're within that tolerance. So even though we don't know exactly what it converges to, we can go as close as we want and still get an answer that will work for us with whatever application we're using it for. Understand? Okay, so that theorem's there. Maybe I'll give that as a bonus or something. I think that would be a good, bonus on the test or something. All right, moving along. Today's going to feel like a marathon. We're just going to keep going and going. What's that? Marathon. Marathon, yes, not miracle. Okay, power series. So all those tests that we did and everything that we've worked with so far has been kind of a build-up to help us be able to deal with what are called power series. If you go back and look at every series that we've done up to this point, if I ask you to actually add up the sum, you could do what we just did, right? And find numbers and number, add them up and get an answer. With power series, we're going to add one more element to the series that we didn't have before. We're going to add a variable. And with that, we're going to create functions. And then we're going to have what are called power series representations of functions. And we'll realize that almost every function we've ever dealt with in our lives can be written this way. And it makes it very easy to work with, well, for a computer. That's the way a computer is going to work. Right? A computer, as we'll see today, computer really has no idea what sine of x is. What it does know is what its power series representation is. And you'll see the advantages of it, but it's going to take a little while to get to there. So first of all, some prelim stuff. Just want to make sure you understand what an absolute value means. If I say the absolute value of x is less than 2, then what I mean is on a number line, the distance between the value x and 0 must be less than 2, which means that you must live on the number line somewhere in here. Now I'm going to write it a different way up here so that you'll kind of see it a little bit, hopefully, more clearly. That's the same thing, right? That's the same expression. X minus 0, absolute value of x minus 0 is less than 2. This is saying, look, the distance, right, the absolute value, look at that as a distance. The distance between some value x and 0 is smaller than 2. So you have x, you have 0. The distance between these two is less than 2. So I can be on the right side of 0, or I could be on the left side of 0. I just have to be within 2 units of it on each side. So what that means is there's another way of rewriting this absolute value without absolute value symbols. You can just write it as a compound inequality. You can say x must be greater than or not equal, greater than negative 2 and less than 2. Agreed? This is the same exact thing as this. We just need to be comfortable converting from an absolute value statement like this into an interval like this. I'll give you another one. How about this? How about 2 times the absolute value of x minus 4 must be less than 3. You know what? Sorry, let's do this. Minus 2 less than 4. Kind of give you a more interesting illustration here. So what we want to do is we want to rewrite this kind of like we did here, right? So what we do is we treat the absolute value almost like a variable, and we try and isolate it first. So what should I do to isolate that absolute value? What's the first thing I should do? I could divide by 2 here, couldn't I? Yes, I could, but if that were a 3, you wouldn't divide by 2, right? So let's just do it another way that would be more standard. I'd move the 2 over first, right? So this would become 2, absolute value of x minus 4 is less than 6. Then you divide by 2, right? And now you're saying the distance between x and 4 has to be smaller than 3, which means that you can be 3 to the left of 4 and 3 to the right of 4, right? Yes? Well, instead of trying to draw a number line and figure out where it is, what we can do is do what we did earlier here. When you had the absolute value of x less than 2, we can just look at this as putting x in the middle, and on the outside, both the positive and negative of this number. So negative 2 on one side, positive 2 on the other. I'm doing the exact same thing here, except I'm going to put the x minus 4 in the middle, and then I'm going to put my inequalities on each side. I'm going to put positive 3 on the right, negative 3 on the left. You see what I'm doing here? And then at this point, get x by itself, you add 4, and you add 4 to everything. So add 4 everywhere, and you get, what, 1 less than x less than 7. So x has to be between 1 and 7. If x is between 1 and 7, that original inequality is true. All right. So now, let's talk about power series. A power series about x equals a. Okay, so that's the way you say it. A power series about x equals a. You might also hear someone say centered at a. Is a series with this form. So any power series centered at a or about x equals a has to look like this. Sum n equals 0. Okay, we start our index at 0 for power series. And I know that that goes against what we've said. We always said that n is going to be, starting out positive integers starting at 1, but it really doesn't matter where we start our index. And we could always shift everything around by just changing. I don't know if that makes sense, but I could always start an index at 0 and change the series function or the sequence function itself, adjust it to compensate for shifting it over 1 on the index. So that's not a big deal. We want to include 0 though because of the factorials. We want 0 factorial to come into play with power series. So that, and then c sub n x minus a to the n. That is it. Now, let me talk about what each of these little pieces are. C sub n is a sequence of numbers. It's kind of like A sub n has been for us in the past, right? A sub n was always the thing that was, being controlled by n and changing. It was usually a number, wasn't it? That's now represented here as C sub n. I think we use C because we're trying to get the idea of that's always going to be some sort of constant, but it's not going to stay constant the whole time. It's a constant that changes throughout the series. And then what we have is a linear expression in x, don't we? X minus a. That's a linear expression in x, but raised to the nth power. So if n is 0, what is this right here? If n is 0, that's just 1, right? And then we would have c sub 0, which would be some number. So we'd have some number in front of 1. Then we go to n equals 1. When n is 1, we'll have some other number, right? And then we'll have x minus a to the first power, which will be just a linear expression. Then we go to the next one, and then we'll have a quadratic, a squared expression in x, right? Then a cubic in 4th degree, 5th degree, 6th degree. You'll have basically a bunch of powers of x, won't you? And so you have a series of powers of x, which is why we call these power series. It is a series of powers of x. All right, a here is a constant. And that a stays the same the whole time. That a is not controlled at all by the index on the summation. So whatever that number is, it's locked in. All right, so let's write out the first few of these, what these would look like. We already said, I talked through it, but first one would be c sub 0, x minus a to the 0. Then it would be what? C sub 1, x minus a to the first power. I don't need to write the first power, but I'm writing it. C sub 2, x minus a squared. C sub 3, x minus a cubed, and so on and so forth forever and ever and ever and ever. The question becomes, if everything in here is defined, so somebody has told you the C sub n, so you know how to get all these C's, C0, C1, C2. So someone has actually defined a sequence in there for C sub n, and somebody has given you an A, right? Then you're going to have a bunch of powers of x here. The question is, for what values of x will this converge? And for what values of x will it not converge or diverge? So it's the same question we've been asking before, except that there's a variable in the problem the whole time, and you have to somehow control that variable to force convergence to happen. That's a major difference between what we've been doing. Because before, it was just converge or diverge. Here, we have to determine how to define x in order to force convergence to happen. All right. Let's do an example before I tell you what's possible with this, because there's a lot of things we have to get into technically with that series. But I think if we start with the basic example, it'll serve us well. So how about we define a power series here as an example. Define C sub n to be equal to 1 for all n, and let a be equal to 0. So I'm defining a power series right here. I'm telling you what the sequence is, right? I'm telling you what the C sub n's are. I'm telling you they're always the same every single time. 1, 1, 1, and sitting in front of all those things. And then I'm letting that, where it says x minus a, I'm letting that a be 0. All right? So let's write out the series. Sum n equals 0 to infinity. C sub n is 1 times x minus 0 to the n, which is just sum n equals 0 to infinity of x to the n, isn't it? Anybody recognize that series at all? P would have, P series, the n would be in the base, and the power would be fixed. Here, the power is the thing that's changing. What series did we, geometric, right? My question, is this geometric? Let's see. Geometric, our idea of geometric was this. N started at 1, didn't it? And it was a r to the n minus 1. Agreed? My question is, are these somehow connected to each other? Let's see. Let's first start out by doing this switching of the index. Like I told you, n could start at 0 and it's okay. Let me show you, and we're going to keep using this throughout for the rest of however long we're together, okay? I would like to see if I can make a geometric series that looks like this actually start at n equals 0 instead. So please pay close attention to what I'm going to do to make this n be a 0. What I would like to do is rewrite this right here, making the right side of it a 0. So if I replace this n right here with n plus 1 and leave the right side alone like that, so I'm making a substitution. I'm replacing n with n plus 1. Yes? I'm about to do that in this expression, which means I'm going to have to replace all the n's with n plus 1s. How would this series be rewritten? Sum n plus 1 equals 1, a r to the n plus 1 minus 1. So do you see where all I did was replaced my n's with n plus 1s? Do y'all see that? Now, what does this equation turn into? What's n plus 1 equals 1? N equals 0, right? That's the same thing. So that really becomes n equals 0. And this is a r to the what? What's n plus 1 minus 1? N, right? So this right here is an equivalent form of a geometric series. In fact, some textbooks, including ours, mentions this. Let's see, does the formula sheet mention this? No, the formula sheet doesn't mention it, but some formula sheets have both versions. They started at n equals 1, and then they'll show you it at n equals 0. So please be aware from here on out that this is also valid for a geometric series. And if you actually write the terms out, like let n be 0, then let n be 1, and then 2, and write them out what they are, it would match up exactly with this. This right here, everything I've done here, okay, is just a changing of the index, right? I just changed the index over. And I did that because I was trying to see if there was a relationship between these two. Is this series similar to this? Yes? What would the A be for us? 1. And then what's the thing controlled by n? The x is like the r, isn't it? So what we need to realize now when we look at this up here is that this series is a geometric series, right? With a being 1 and r being what? R is x. And what do we know about this about geometric series? It converges if what? When does a geometric series converge? If the absolute value of r is less than 1, right? So this series right here, that series, this will converge if the absolute value of x is less than 1. All right. Let's see if we can get our heads around this a little bit now. I want to take this series up here, this right here. I want to write it down. Like I actually want to write it down, plug in 0, then 1, then 2, then 3. So take sum n equals 0 to infinity of x to the n. This is going to be, plug in 0, what do you get? 1 plus x squared plus x cubed plus x to the 4th plus ... forever, right? If you add these up together, will it converge or diverge? We just said it'll converge if what? If whatever we plug in there, the absolute value of it is less than 1, it'll converge. So what I'm going to say is this. This is equal to, what does a geometric series converge to? What does a geometric series converge to? A over 1 minus r. For us, A was what? 1 over 1 minus what was r for us? X. This series will equal 1 over 1 minus x if the absolute value of x is less than 1. What if the absolute value of x is greater than or equal to 1? It's going to diverge. And think about it. Give me a number that's bigger than 1. 2? What's 1 plus 2 plus 2 squared plus 3 squared plus 4 squared? 1 plus, slow down. 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th plus, right? That's just blowing up. It's getting huge, right? But if we do something like 1/2, then this is 1 plus a half plus a 4th plus an 8th plus a 16th, and that's a geometric series and it will converge. This is a power series, right? It's a specific example of a power series, right? That's one example. If we ever see a power series that looks like that, we know it converges. We actually do know what it converges to, as long as this condition is satisfied. So this is the game we're going to play now, is we're going to try and look at these power series, and we're going to try and figure out what makes them converge, just like we did right here. We were very lucky in this problem, right, because we recognized it as a geometric series. We know that we're limited, though. Right? There are only a few types of series that we could actually tell what they actually add up to be. All right. Do we have any questions? Let me see if they call this a theorem in the book. Yes, it is. It's a theorem, but they don't have a good fancy name for it. This is on page 466. If you want to reference it later, I'm going to put a red star next to it because you have to know this theorem. You don't have to know like why it's true or how they proved it, but you need to know the consequences of this theorem. What it tells you will happen. Given any power series of the form sum n equals 0 to infinity c sub n x minus a to the n. Given any power series, the question is convergence or divergence, right? That's the question. Convergence or divergence. There are only 3 possibilities. One, it converges if x equals a only. Now let's just think about what that's saying. I'm looking at a power series, right? Here it is. All power series have to look like this. This theorem says 3 possible outcomes. One is that it converges if x equals a only. So let's replace x with a. If x is a, what's this? 0, and this is just everything 0, so you're adding up 0 forever, right? What's 0 plus 0 forever? 0. That is finite, right? That converges to the number 0. So if x is a, it converges. The theorem is saying that's one possibility, and if that happens, that's the only thing that can happen. The other 2 things that happen can't happen. So let me write the other 2 so you'll start to see the contrast here, hopefully. It converges for all x. And I'll put element of the real numbers. That I put in there just to kind of stress to you that what I'm saying is that, or what this theorem is saying, is that if you plug any number in here, okay, for x, it will converge. Doesn't matter what you plug in. As long as it's a number, you plug it in, it'll converge. The one we just saw, right, we said that the absolute value of x had to be less than 1, the previous example. Does that mean I can plug any x in and it'll converge? No. So far this theorem is saying, look, it either only converges when you force this thing to be 0, or it'll converge all the time, or the third possibility, it only converges on an interval where the absolute value of x minus a is less than some capital R. And I'll put under here also the interval, because that's an interval, right? This represents an interval. That's what I started this with. Remember, what does the absolute value of x less than 2 mean? It means it's an interval, right? An interval on the number line. Okay, it converges, this is saying it converges on some interval. That interval may be open, closed, or half open. What the hell do I mean by that? What does an open interval look like? Something like, this is a specific example, -1 to 2. That means all the numbers between -1 and 2, right? Not including -1, not including 2. That's what we call an open interval. Closed interval would look like this, -1, 2, closed. That would mean you can include the endpoints, can't you? And then half open would mean one side is open, the other side's closed. You could also say a half closed. They're the same thing. -1/2 to 2, or I said 1/2. -1 to 2, or -1 to 2. So these are both half open intervals, aren't they? A little bit more about this here. The capital R is called the radius of convergence. And if you take -r less than x minus a less than r, that would be, remember I said if you want to turn this into an inequality, you drop the absolute value signs and you put negative r on one side, positive r on the other, right? And then if you want to solve for x, what would you do? Add a to everything. So if I do negative r plus a less than x less than r plus a, this right here is called the interval of convergence. Again, this may be open, closed, or half open. It just depends. We're going to have to work that out for each problem, determine what it is. So little star here, radius of convergence. Star here, interval of convergence. A lot of these problems, what will be stated is, here's a power series, find its radius of convergence, find its interval of convergence. Those are things that are going to be asked. So this is a great theorem, and let's think about why it's a great theorem. It's saying that for every power series, it's only going to converge at x equals a, right? Which is a point, right? A single point. It's only going to converge at a single point. Or the second part's saying what? It's going to converge on the entire number line, right? Everywhere. Yes? Or the third thing is saying it's going to converge on some interval in here. Now that interval again could be closed, open, or half open, right? That's it. For all power series, you can only have those three possibilities come out. And that really saves our ass a lot, because think about it this way. What if this theorem didn't exist? And I figured out that it converged on some interval. How would I know that that's the only place it converged? Like, what if maybe there's another interval somewhere else where it converges also? But as soon as I find that first interval, boom, that's it. That's the only one that can exist. You're limited to only one. Or if you determine that, you know what, it looks like it's only one point, how do you know that's the only point? Well, because it says that if it's going to be a single point and not an interval, then you can't have a single point with an interval. It's just a single point. So this is good news for us moving forward with these. So let's do an example. All right. Find radius of convergence and interval of convergence. Here it is. Sum n equals 0 to infinity, negative 5 to the n, x to the n, over the square root of n plus 1. You're about to see in this example why on your final you are not going to have a lot of problems that are not power series. You'll see in this problem why when we get through. It's going to take us a while to get through this whole thing. But if this was not here, okay, look right here, if that x to the n, if that was not here, that would be a series problem, not a power series, right? That would be a series problem. And how would you attack that problem as a series by itself, not power series? What type of series does this look like to you? It's alternating series, right? So maybe the alternating series test. Maybe that would work. But that's not what we have to do. Or you could do ratio test or something like that. I mean, you've got a lot of tools in your toolbox when it comes to series. But now we have a power series. So the standard test for power series, the one that works most of the time, is the ratio test, because the ratio test deals with these powers well. Because when you set them up with ratios, you'll always get good cancellation. So here's what I want. To figure out where this converges, I want to know when the limit as n goes to infinity. Anybody remember what the ratio test says? We put one on top of the other one. Which one? What was it? A sub n plus 1 over a sub n. I want to know when that's what? Ratio test gives us convergence when? When that's less than 1, right? I would like to know when the absolute value of plugging n plus 1 into this divided by the absolute value of plugging just n into this, when that ratio yields, well, the limit of that ratio yields something less than 1. When that happens, I have convergence, don't I? Now, a sub n plus 1 is the whole thing, all right? It's the whole expression. I mean, plugged in with n plus 1s, but it's everything. So let's write this out. You're going to need some space here. All right, let's plug in n plus 1. We get negative 5 to the n plus 1 times x to the n plus 1 over the square root of n plus 1 plus 1. I'm supposed to divide that now, right, by what I get when I plug n into this expression up here. But remember we said since you're going to divide, you're going to wind up flipping it anyway? Remember me saying that with ratio test, you're going to wind up flipping it? So next to this, with multiplication, what should I put on top? Square root of n plus 1. And on the bottom, negative 5 to the n x to the n, right? We want that to be less than 1. That's what we're looking for, right? Trying to figure out when that limit's less than 1. And even though this looks kind of like a disaster, a lot of things are going to start canceling out and becoming good. So because this is my first example, I'll show a little bit more detail. This is negative 5 to the n times negative 5. This is x to the n times x all over square root n plus 2 times square root n plus 1 over negative 5 to the n x to the n. I want this to be less than 1. So I'm going to have to figure out what all this limit is and make sure I can force it to be less than 1. That's just using properties of exponents on these, right? That's all I did. Just rewrote these up here like this. And you see our cancellation? Negative 5 to the n, negative 5 to the n is gone. X to the n is gone, right? Now, the standard practice here is to put all your n stuff together on one side and your x stuff together on the right side inside that absolute value. So that's what I'm about to do now. Limit n goes to infinity. We have, what, negative 5 root n plus 1 over root n plus 2 times, now what x stuff was left? Just x, right? Like this? The reason why I split it up is because the limit is only affecting the stuff with n's, right? It's not really impacting this x at all. So I just have to figure out what this limit is. So if you just focus all your attention right here, You get what on top, if you let n go to infinity, you get infinity up here and you get infinity down here, don't you? And you could do L'Hopital, but then you have square root. So I think what I'll do is I'm going to rewrite something. See if you believe me or not on this. All right. So the first thing I did was, because this is an absolute value, I can just take the absolute value of 5, the absolute value of negative 5. The absolute value of negative 5 is 5, right? So I don't need the absolute value anymore. And then this over this is always a positive number, so I don't really care about the absolute value around that because it's always positive. And when you have a square root, a fraction that has root on top and bottom, you can turn it into one fraction, right? And then put the root over the whole thing. I like this because right here I get infinity over infinity, and then I can do L'Hopital on that one time, on the inside of the root. And then what would you get in there? You get 1, and then you have a 5 on the outside, don't you? So by L'Hopital on this, I take the limit now. The limit is gone now, isn't it? I'm going to have a 5 times 1 times absolute value of x less than 1. So this equals, or I should say, I shouldn't have these equal signs here. It's bad notation, sorry. Erase these equals. Make them more like arrows. This implies this is true, which implies this is true, which implies this, right? Which implies that we want 5 absolute value of x to be less than 1. No more limit, right? And now this is what I started power series with. We need to understand how to work with this. Let's divide both sides by 5. Absolute value of x less than 1/5. Okay, now we wanted 2 things, radius of convergence and interval of convergence, right? The radius of convergence is when you get it to look like this. The absolute value of x minus a is less than some number r. That number r is your radius of convergence. We have the absolute value by itself. What does it appear a is for us here? 0. And so this 1/5 looks like our capital R, doesn't it? So our capital R, our radius of convergence right now, is 1/5. Now, the interval of convergence we get by converting that into an interval, which is just negative 1/5 less than x less than 1/5. We good with this? No questions so far? What we're saying is so far in this point, or up to this point, is that as long as the x value we plug into this nasty thing, as long as the x we plug in right here is between negative 1/5 and positive 1/5, this series will converge. But there's something we have not talked about. What did I tell you about the interval of convergence? It could be what? Open, closed, or half open, right? The ratio test tells us we have convergence when what? Ratio test convergence if L is less than 1, right? Which is why we use less than 1. What does it tell us happens if L is equal to 1? The test is inconclusive, which means it could still converge, couldn't it? So we actually are not done because we have to figure out what happens when these are equal. That means when you're at the actual endpoints of the interval. I need to now go test what will happen if I let x be negative 1/5, and I have to test what happens when x is positive 1/5. This is a step that students will forget to do, and you lose a lot of points because this part of it, great, that's good, you do the work here, everyone's happy, but you still haven't figured out what happens on the boundary of the interval. The boundaries. Y'all heard of a guy named Ted Kaczynski? Y'all remember Ted Kaczynski? Heard that ring? also known as the Unabomber, right? The Unabomber, who's like sending packages through the mail, bombs in them and stuff. They couldn't find him for a long time. They finally found him, right, in some shed out in the wilderness. He was a math major. One of his major, I guess, interests were boundary value problems. Now, more complicated than this, but like what happens along the boundary of things. A lot of times we can tell what's happening on the inside and on the outside, but along the boundaries is where things can become really kind of challenging. Like here, because we're only looking at a number line, the boundary is only 2 endpoints, right? Yes? Imagine if you could, though. I'll do it on the board so we don't get all that. I'm going to go off on a tangent. I'm trying not to spend too much time here, okay? There's a function, right? And if I plug in any number between 0 and 2, it's well-defined. And if I plug in 0 and 2, it's well-defined. Yes? That's a very well-behaved function. But our input, right? Our input is just a number off a number line. So it's very easy for me to investigate what's happening at the ends or the boundaries of this interval because there's only 2 places to check. Yes? Now imagine you have a function, and most of you have not seen any function like this before, but when you take Calc 3, you will. Now instead of having a single input, you have 2 inputs. You have not only an x, but a y. So your input doesn't look like a number line anymore. It now looks like what? A flat sheet of paper. And so the input that I put in can be any ordered pair on this page. So let's say that's the point 1, 1. I plug in 1 for x and 1 for y, right? 1, 1, you get in there, you get 2, right? It's well defined. Yes? What does a closed interval look like here? It's not the same as over here, right? So imagine you have a region of space like this. Now you have not an interval, we call this a set, right? A region. And if I want to know what's happening on the edge, I'm looking at this outer edge, right? That's a much more challenging problem than this one, because this was only 2 points. This is infinitely many points, isn't it? And so I'm either going to include the boundary or not include the boundary. If I don't include the boundary, I make it usually like a dashed boundary, like this, or it's solid. And then you can get more complicated regions where you have like a region that looks like that. So now it's like a donut, so you have to look at the outside and the inside, and so we have to start understanding what these 2-dimensional sets look like, and we have ways of defining them. Open, close, we call them connected, simply connected. There's a bunch of stuff. And then imagine you have a function that goes and takes on 3 variables in. Now your input is 3-dimensional. Your output would be in the 4th dimension, but it would not be a 4-dimensional output. The output would just be a number, right? Well, if I define it that way. I could say x, y, z, right? Just multiply the 3 inputs together, spits out a number. And so, but your domain is 3-dimensional. Well, just imagine like a ball in here. But it doesn't have to be a ball. It could be like a blob. And what's the boundary of the blob look like? And how do you study the boundary of the blob? Understand the difference here? And so, let me get back to this. I know I'm already gone. I'm already off that tangent. This is a function that goes from R into R, which means you had 1 input, 1 output, right? Number in, number out. This one goes from what? 2-dimensional space into 1-dimensional space because it spits out a single number. So when we are back here, when you go from R into R, if you want to visualize this function, you need 1 dimension for the input and 1 dimension for the output. So we graph it, don't we? Parabola. Input is the x-axis, output's the y-axis. Here, in order to visualize this, you would have to have 2 dimensions for the input, 1 dimension for the output, so you need 3 dimensions. So we could visualize this as follows. The x and the y would be the input, the output would be our z-coordinate, If you were to graph a function like this, it would look like a surface. It would look like a blanket waving around in the wind or something. All right? Then you get to something like this. You need 3 things for the input, 1 for the output, right? You need four dimensions to visualize this. It's not happening, right? Yes? It's not happening. And then what stops you at 3 inputs? Why can't you have 4 inputs? Or 5 inputs, right? So you get a computer model, right, that's trying to predict weather. Do you think they just go out and take the temperature and the humidity and that's it, just 2 inputs? Those computer models have many inputs, right? And then there's a function that somehow gives you an output. But there's nothing that stops you even there. What's to say you can't have an input, a function that has 3 inputs and spits out 2 outputs? I mean, two outs. So how about x, y, and then x squared minus z? How about that? So you plug in a triple, right, an ordered triple from 3-dimensional space, R3 is what goes in. It spits out what? Not a number, but an ordered pair in 2-dimensional space, right? So you can basically go and have a function that goes from any dimensional space into any dimensional space. All right, sorry. That's right. In vector calculus, what you do is you realize you just do it all with vectors, and it's a little easier to work with. And then your dimensions makes a little more sense because vectors, we have something called the dimension, and yep. So there's no restriction on what dimension you can go from into what dimension comes out. There's no restriction. So Cal 3, vector calculus, what you do is you just say, hey, everything we've done so far has been that first case right there, pretty much. Right? R to R. And in vector calculus, you say, now let's go further and see how the calculus behaves. Does the calculus still behave the way it behaved before? Turns out a lot of things stay the same, but they're just more complicated. So here, here, I just don't want you to forget how important the next step of the problem is, which is to check the boundaries. If you don't check the boundaries, you're missing half the problem. So now I must check when x is negative 1/5 and when x is positive 1/5. And what's good about this is we actually get to replace x. We go back to the original series. So let me start with x is negative 1/5. Go to the original series. It was negative 5 to the n, right? Then it was x. What was x? What am I replacing it with? Negative 1/5 to the n over square root n plus 1. Is that right? Yes. I've replaced the x here, haven't I? Since both of these are to the n power, can't I put them together? Does everyone realize this is no longer a power series? This is now just a series. So what is that? What's negative 5 times negative 1/5? It's just 1, right? 1? 1 to the n? 1 to the n? Which is just 1. So isn't that just 1 over square root of n plus 1? So what do you want to do with that? It's really close to a p-series, isn't it? If that was just square root of n, it would be a p-series, wouldn't it? It would be p is 1/2. And what happens if p is 1/2? Do you remember? P-series diverge. It would diverge, right? But you can't say that's a p-series because of the plus 1. So instead, why don't we compare it to a p-series? Compare it? And let's use, how about the limit comparison one? Because that was the one that seemed to always be the nicest one. What do we need for the limit comparison? Using limit comparison, I'm going to compare to what I'm calling my 1 over root n series, which is a p-series, p being a half, which diverges, right? I'm going to compare it to a divergent series because I'm pretty sure this one diverges also, right? So I take the limit as n goes to infinity of my series, right, which is 1 over the square root of n plus 1, over the series I'm comparing it to, 1 over root n, and then I just reciprocate and what does that limit turn out to be? You do one root, just a single root again, put them all together under one root. Then what's the inside? N over n plus 1, infinity over infinity. L'Hopital once, that's 1. Square root of 1 is 1. So this should turn out to be 1. What's the conclusion? This number 1 is a constant, right? Positive constant. Then whatever the series you compared it to does, ours will do, right? You understand? Now, there were some conditions that we had to have that I didn't write down here. Comparison test. Both of the series had to be positive, which they were, right? That's about it, right? I didn't state it, but I just want to make sure you're aware. If this were an alternating series, we couldn't do this test. We good? Conclusion? Our series does what? Does what? Diverges. So in the big scheme of things, remember what we were trying to figure out was on this interval, what happened at negative 1/5. What we figured out was that at negative 1/5, this series up here turns into this, and that's divergent, which means that negative 1/5 should not be part of our interval of convergence, should it? Should not. Okay. Now we need to do what? Test 1/5 instead of the negative 1/5. I'll put under here just so we are keeping track of things. So x equals negative 1/5 is not in the interval of convergence. That side's going to be open. The question is what's going to happen on the other end. Is the 1/5 going to be included or not included? So let's check it out. So if x is positive 1/5, negative 5 to the n, 1/5 to the n, all over square root of n plus 1. What does that turn into? Negative 1 to the n, right? This time, that doesn't just turn into a 1 because it's alternating, right? Negative 1. So how do you want to handle this one? Alternating series test, right? It's an alternating series. Let's go for it. With the alternating series test, I want to show what two things? Wasn't it a sub n is greater than or equal to a sub n plus 1? And the second thing was limit n goes to infinity, a sub n equals 0. I need to show that it's a decreasing sequence. I need to show that the limit goes to 0. And when I say it, a sub n, I'm only talking about which part of it? The positive part of it, right? Not, remember with the alternating series test, you ignore the negative part. You look at the remaining part, which I'm calling a sub n here. That's 1 over root n plus 1. So take a look at that. Does the limit go to 0 of this? Yes, so that I think I can check just by looking. How about the decreasing part of it? Is this decreasing? Yes? How would you show it? I mean, there's kind of two ways you could do it. You could do, is 1 over root n plus 1 bigger than or equal to 1 over root n plus 1 plus 1? You could work this inequality out, couldn't you? And figure out that it's true or not? Another way, wouldn't another way be to take the derivative of this and show that it's always negative? You could do that also. Take the derivative of this, treating it as a function of x. I like the derivative way. If I rewrite that as n plus 1 to the negative 1/2, so I bring this thing up, and then take a quick derivative. Negative 1/2 n plus 1 to the negative 3/2, which is negative 1 over 2 square roots of n plus 1 cubed. So I'm just using properties of rational exponents. This is the same as this. This is always negative, isn't it? Yeah, that's a derivative here. So that's always negative, because this is always positive. Cubing, it's always positive. Square root of positive number is positive. 2 times a positive number is positive. So the bottom is positive, top is negative. And so therefore, you have a negative derivative. Negative derivative means decreasing. This is decreasing sequence. So either way. So wait a minute. You mean to tell me that if you are asked for the radius of convergence and interval of convergence on a power series, you not only have to do ratio test, but there are two other points you have to check, which may turn out to be two other tests? Yes, that's what I'm telling you, which is why these are usually all I need to give you on a test. Because I'm kind of knocking out 3 birds with 1 stone, right? Ratio test, alternating series test, and a comparison test all in one problem. So it really tests whether or not you know the tests, right? All right. Good problem. We're not done. We need to write the final conclusion. So, interval of convergence. The interval of convergence is negative 1/5, do not include, right? X, do we include this endpoint? Did it converge? Yes, we do include that. So you could write it that way, or you could write it this way. Right, both of those are acceptable answers. And if you really want to get in there, you can say like X is an element of that interval. Now, please keep in mind that on a test, if I ask you for the radius of convergence, and only the radius of convergence, there is a significant amount of work that you do not have to do, right? You would have been done earlier when you just had 1/5, right? Right there, 1/5. All the radius of convergence tells you is from the point that you can pick to the left and to the right, how far can you go? 1/5, right? It does not tell you about the endpoints. All right, I'd like for you to start getting this one going, okay? I'm going to see how much you can do working on your own. I want both find capital R and let's call it capital I for interval of convergence, all right? Find R, the radius of convergence, find the interval of convergence. So just to help you get started, because I know this is only the second example of this, what's the first thing you're going to do? You're going to set up the ratio test. You're going to make sure that you set up the inequality less than 1. Work it all out. Start separating out your n's from your x's. Take your limit, see what happens. And then maybe you'll have endpoints to look at, maybe you won't. You should have at least this. That's setting up the ratio test. You replace your n with n plus 1 here. Then you just rewrite this flipped over here. Rewrite 3x minus 4 to the n plus 1, splitting it up. Expand this out. N plus 1 squared is n squared plus 2n plus 1. Then add 1. Oh, that should be 2. Thank you. And then you should get your canceling here. And then you're going to split up what? Your limit of what? You've got 3. What should you split off is what I'm getting at. The x parts, which will be the 3x plus 4. And then you're going to put that with the n stuff in front. Shit. Okay, so the n stuff is n squared plus 1 over n squared plus 2n plus 2. Then your, do I need absolute value around that? No, I'll take the absolute value, but I do need the absolute value around the x part, which is 3x minus 4. Need that to be less than 1. What is this limit? It's going to be a 1. So you do L'Hopital twice, and you get, what, 2n over 2n plus 2, and then L'Hopital again. And so you just get a 1 there. And so you're left with just this. So for radius of convergence, we need it to look like this. X minus a less than capital R. So what's important here is you need a 1 in front of the x. So I'm going to factor out a 3 from both of these. Pull a 3 out. Like that. And then divide both sides by 3. So just be careful on that step right there. Because you may say, oh, my radius of convergence is 1. It's not 1, it's 1/3. Understand? It's capital R. It's 1/3. Now for the interval of convergence, what I'm going to be doing is looking at negative 1/3 less than x minus 4/3 less than 1/3. So I'm just turning the absolute value into a string of inequalities. Let's add 4/3 to both sides. So what happens if you add 4/3 to negative 1/3 there on the left? Just get 1 less than x, less than, add 4/3 to 1/3, 5/3. So you'll be testing two endpoints here. So let's start by testing 1. Can I move on? At x equals 1, the original series becomes plug a 1 into the original series, and what do you get on top there? -1 to the n. On the bottom, n squared plus 1. And to save us time, I'm not going to go through it. The alternating series test, on a test you would have to show it, right? The alternating series test, you have to show it's a decreasing sequence. You have to show the limit goes to 0. You could show that that works. It converges. Then you have to test x equals 5/3, which is sum n equals 1 to infinity. What happens when you plug 5/3 in there? You get 1 to the n? I'm sorry, yeah, 1 to the n, but 1 to the n is just 1. So you get 1 over n squared plus 1. And how would you do that one? That compare it to a p-series, right? That looks like a p-series with p being 2, right? So if you compare to 1 over n squared, then your conclusion that you should draw is it does compare. And since that one converges, this one also converges. So since it converges at both endpoints, my interval of convergence should contain both endpoints. So I will be 1 to 5/3. That's it. Does this make sense? It's just inequalities and limits and just keeping track of things. Any questions? See if I can bring up this power series thing real quick for you. This is the one we just did, I believe. All right, so this series, I'm having the computer do this for us. It's going to start adding up things for us, all right? So here's the series. I don't know why I don't have the n squared plus 1 down there. But right now, I'm replacing the x value with 2. So I'm putting a 2 in here. I'm figuring out what happens. Right now, the nth partial sum is -5. If I start adding up, what's going to happen if I start adding more and more? What should happen to this number? If my x value is -2, according to what you just did. Is -2 inside or outside the interval of convergence? It's outside. So if I start adding these up, what should happen to this number? It should get divergent, right? Look at it. See it? Oh, it's getting huge fast, isn't it? All right, so let me back it up. Let me pick something that's inside the interval of convergence, which was what? Between 1 and 5/3? Yes? So how about 0.95? That's not in the interval of convergence, right? So let's see what happens. 0.4, 0.38, 0.42. It looks like it's converging. Let me go pretty far out with this. See how it's now at 0.57? I mean, it took me a while, but it's not getting closer to something. It keeps on spreading out. And now let me go inside the interval of convergence, 1.4. Oh, look at that. It's already converged to something. I'm already within 6 decimal places of the true sum, right? Okay. This is the one we're doing next. It's called an order 0 Bessel function. This is used in like wave, like when you hit a drum and you've got the wave pattern on the drum surface. It can be modeled using Bessel functions. And so we still haven't graphed any of these because we actually haven't even talked about the fact that a power series can be a function. That's the next thing. But let's just look at this order 0 Bessel function and see if we can find out its radius and interval of convergence. So your next example, j sub 0 of x equals this sum, -1 to the n, x to the 2n over 2 to the 2n times n factorial squared. Order 0 Bessel function. Here's kind of the way I want you to think about this, even though I'm about to talk about this after we're done. If I give you a function over here, f of x is the square root of x. This is a well-defined function on its implied domain. What's the domain of this function? Well, your x has to be greater than or equal to 0, right? So it looks like this. That's your domain. As long as x comes from this domain, this function is well-defined, right? When we have a series, power series, we are figuring out the x's that make it defined, right? That give us a convergent number. So if we take a power series and we define a function as that power series, the domain of this function is what? The interval of convergence, right? The interval of convergence is the domain of that. So that's what we're going to do right here. And so my terminology, when I ask you something here, I'm not going to say find the radius of convergence and interval of convergence. What I'm going to say is this: find domain. Because there might be some x values that you plug in here where this series diverges and therefore it's not defined. I'm looking for the x values that do give you a number out as an output, and that would be considered the domain. So understand how domain now means interval of convergence for us? Yes? All right, so here we go. Limit n goes to infinity. Ratio test. Almost 100% of the time. Yeah, I mean, it's for power series, it's the way to go. And the reason why, again, is because all power series are going to contain an x to an n power. And so you're going to, get that cancellation to happen all the time. All right, so let me see if I can go a little faster with this. -1 to the n times -1. Are you okay with me taking this x to the 2n and rewriting it as x squared to the n? Is that all right? Is that the same thing? Yes? So how about when I write this next one, I write x squared to the n, and then what next to it? +1. I'm going to go ahead and write it out, though. X squared? You'll realize I'm not writing the n + 1. I'm actually splitting it off on the first step. Saves me a little time. Over, and then I could rewrite 2 to the 2n as what? 4 to the n, couldn't I? 4 to the n? So this is 4 to the n times what? 4, just 4, okay? And then This one I can't really get around. This is going to be n plus 1 factorial squared. Notice my use of parentheses. I'm replacing n with n plus 1. So the factorial will be acting on the entire n plus 1. Then I square the whole thing. Everyone agree that that's what I get when I plug in n plus 1? Okay. Now on the other side, I'm going to write the original sequence there flipped over. And I will change some things also. I'm going to write 4 to the n. And then I'm going to write n factorial squared. And then on the bottom, negative 1 to the n. And then x squared to the n. I want that to be less than 1. And so I get some canceling here. And I had a pretty awesome weekend. I went to Arizona and went hiking. And we were on this peak of this little thing. They call them mountains. They're not really mountains, but and we went off the path to this really cool like hole in this rock, and it was beautiful. And I got attacked by bees. I got stung all over this arm, man. It just will not stop itching. So I was thinking I was all being adventurous and stuff, and they didn't want me there. They didn't want me there. Okay, cancel here, here, here. What else? 4 to the n. There. Can I do anything with the n factorials? It's got to be something I can do there, right? Can I peel off on this n plus 1 factorial? Can I peel off 1? Can I rewrite this as n plus 1 times n factorial and then squared like that? Could I do that? And that's what n plus 1 factorial means, right? N plus 1 times n factorial. And then couldn't I write that as n plus 1 squared times n factorial squared? Because there's multiplication between these. If I square something with multiplication, I just square each one. So I could do that. And that's great because that would cancel this one and this one, wouldn't it? All right, so what is left on top? What's still up here? Negative 1 x squared. Now, it's in an absolute value, isn't it? So the absolute value of negative 1 is just going to become a 1, so I don't care about that. So I have an x squared. I'm going to throw that over here, absolute value around it. And then that means I still had a 1 on top, didn't I? And then what was on the bottom? I had the n plus 1 squared, right? And a 4, didn't I? So 4 n plus 1 squared. Yes? I want that to be less than 1. Now what? We haven't seen this. Let n go to infinity, and what does that first piece become? 0. So think about this. You pick an x, right, to see if it converges? And when you do that, you always are going to have to let n go to infinity. So it doesn't matter what x is, because that first part's going to go to 0. You can't pick infinity for x, right? You have to pick a number. So no matter, as soon as you fix that number, this thing in front of it goes to 0. It's going to kill the whole thing off, right? It's going to make this whole thing, right? This whole side right here is going to go to 0 after you take a limit. Is that less than 1? Always, right? That means that, what? It converges all the time, right? Remember, there were 3 possibilities. We either had a single point, or we had an interval, right? Or we had everything. Actually, the way I gave it to you in the proper order, I said a single point everywhere, or on an interval. In this case, doesn't matter what x is. So the radius of convergence is what? How wide is our interval? It's infinite. So we actually say our radius of convergence is infinite. And the interval of convergence, which is equivalent to saying the domain of this function, is what? Negative infinity to infinity. Hey, this function is defined everywhere. It's a Bessel function. That's kind of why it's a great one, because it has an infinite domain. So you want it to behave all the time, and it behaves well all the time. So if I were to come back to this and kind of, plug in different x values, it wouldn't matter, would it? Any x value I pick, when I start going out on this, it's going to converge. Whoa. Okay? All right, I think we take a break. So we'll say 10 after. We come back, 10 after. I think it's going to be very heavy with this. Yeah. We'll have to talk about it when we get to it. Yeah. Okay, back to it. I have another example here. That's the homework assignment for this section. I'm going to give you 2 more examples, and then we're going to move on. For this one, we haven't seen this. That's why I wanted to show it to you. First, you plug in n plus 1. So again, let me see how quick we can do this. N plus 1 times n factorial x to the n times x over, so I replaced n with n plus 1. N plus 1 factorial is n plus 1 times n factorial. I already split it apart because I know I'm going to need the cancellation. And then x to the n plus 1 is x to the n times x. Now notice we don't have a fraction here. So when we actually come through and divide it by the a sub n, we can just do the division right now. We don't have to write the reciprocal because there's no fraction. So n factorial on the bottom, x to the n. Is that clear? You understand? Yeah? All right, we get our n factorials to cancel, our x to the n to cancel. And so what you're left with here is a limit as n goes to infinity. The only thing that has n in it is n plus 1. And then next to it, I have an x. I'll put in an absolute value. I need that to be less than 1. But what happens here as n goes to infinity? It becomes infinite, right? This becomes infinite no matter what we choose for x. Because again, once we fix x, that thing's going to blow up, except if we do what? What's the only choice we can make for x that would make this thing stay less than 0? If x is 0, right? If we choose x to be 0, it is exactly 0. Then it doesn't matter how big this ever gets, because a huge number times 0 is 0, right? Don't confuse that with this. When we do a limit infinity times 0, that we said was indeterminate form, didn't we? But that, what we meant was, this was going to this, right? Going to infinity, and this one was going to 0, headed towards there. There's a difference between that and saying that one of those is 0. If it is 0, then it doesn't matter. So the only way we can get convergence is if x equals 0, we get converges. Otherwise, it diverges, doesn't it? So that means that we only have one point where it converges. Remember, there are 3 possibilities. This is that possibility we hadn't seen. So curious, What's the radius of convergence if you have a single point? What do you think? How wide is a single point? 0. A single point doesn't have a width to it. So the radius of convergence is 0. The interval of convergence isn't actually an interval, it's a point. So we would say interval of convergence is actually just x equals 0, which is a point. Understand? So in all these problems, we're either going to get some interval where we have to check the endpoints, we're going to get everything, like the Bessel function, or we're going to get a single point, which means the radius of convergence is 0. All right, on the next example, this one I wanted to show to you because it's kind of a different notation that we haven't really played a lot with. N squared x to the n over 2 times 4 times 6 times ... all the way till we get out to 2n. See, the bottom is kind of like a factorial in terms of like you go out to a certain spot, you're multiplying something times something, but it's not 1 times 2 times 3 times 4. This is the product of your even numbers starting at 2. So 2 times 4 times 6, and then you'd stop when you get to 2n. So let's, just so you're clear on the notation here, what would this sum actually be? Like replace n with 1, and what would you have? On top you'd have x. On the bottom you'd have 2 times 4 times 6, but you actually are supposed to stop when you get to 2n. And what was n? We would 1, so you would just go 2 and stop. So it would just be 2. Then plus, now plug in 2. So up top you get 2 squared, 4x squared over, now you go 2, 4, 6 until you get to 2n. So you stop at 4, so 2 times 4, which would be 8. I'll do one more. Plugging in 3 squared, 9x to the third over what? 2 times 4 times 6? 48. So, and then you can keep going. I just wanted you to see how it works, all right? What we need to do is figure out the radius of convergence and interval of convergence. So we're going to do our limit. We're going to let n go to infinity. Since we have a fraction, I'll set up my ratio. So let's try and do this, replacing n with n plus 1, n plus 1 squared, x to the n times x, over, and here's the tricky part, 2 times 4 times 6 times ... times, now, I'm replacing n with n plus 1, right? So replace this n with n plus 1, the 2 would distribute it through it, wouldn't it? So it'd actually become 2n plus 2. So the last one I'm going to have is 2n plus 2, wouldn't it be? And because I know what's about to happen, what would the one right before that be? Just 2n, right? Just 2n? Because each one, what's happening is that each one of these is going up by 2, right? 2 goes up to 4, then up to 6. So if this is 2n plus 2, the one right before it is 2 less than it. So the one right before it is 2n. Understand? Now rewrite the original flipped over. 2 times 4 times 6 times ... all the way out to 2n over n squared times x to the n. I want all of this to be less than 1. Questions, comments? Cancel, good cancellation here. 2, 2, 4, 4, 6, 6. all the way out to 2n. You see why it was important for me to write that one before it? It just to help me see where it cancels what's left. I've got an x to the n's gone. I can't cancel the n squareds, can I? Because this one's stuck in a parentheses. So at this point, I think what I'll do is I'll throw all my n stuff together and then all my x stuff together. Limit, n goes to infinity. Okay, in terms of n, what do I still have on top? N plus 1 squared. Let's go ahead and just FOIL it out. It's n squared plus 2n plus 1. I don't need an absolute value about that because that is positive. And what else is on top? X. I'll throw that over here. On the bottom, what do I still have? N squared times 2n plus 2. So how about we distribute an n squared through here? We get 2n cubed plus 2n squared. There's a multiplication between that. And then I have all that needs to be less than 1. You with me? What happens? L'Hopital. 0. Which means it doesn't matter what I pick for x, right? This is going to go to 0. That's always going to work. That will always be less than 1. So what is your radius of convergence? Infinity. What's your interval of convergence? Negative infinity to infinity. All right. So the problems here that I gave you for homework are a good mixture of where sometimes you're going to have this, sometimes you're going to have a single point, sometimes you're going to have an interval. Just remember, if you get an interval, that you make sure you do the inequality correctly. Because if you get the two endpoints wrong, then your two tests are going to be for the wrong places. So just take your time through that absolute value conversion over to the interval. All right. 8.6. Representing functions as power series. This section is exactly what it says. We have a function. We want to somehow convert it to a power series. Represent the function that we're familiar with as a power series instead of what we're familiar with. So we'll start out with an example. Well, before I proceed, I'm just going to have you recall. We're going to rely heavily on this as we start. Remember that sum n equals 0 to infinity of x to the n, which was 1 plus x squared plus x cubed plus dot, 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 was equal to 1 over 1 minus x if the absolute value of x was less than 1. That was the geometric series that we did just a little while ago, right? Just remember that. And now what I'd like for us to do, so I'd like for us to represent, or I'm just going to say write as a power series. And find I, the interval of convergence. Everyone okay with me just using I for interval of convergence instead of having to write that over and over and over? So here's the function. before I do this, keep in mind, with the geometric, what happened if the absolute value of x was 1? What happened? What happened? If it was 1 or bigger than 1. It's on your sheet. For geometric series, the absolute value was bigger than or equal to 1, it diverged, right? Now, the reason why I'm saying that is because, remember, for interval of convergence, we had to test the endpoints. If it's a geometric series, you don't have to test the endpoints because you know at the endpoints it diverges. Just keep that in mind. All right, so look, this right here is a function, right? I can tell you right now, plug in 2, right? And you would get, what, 1/5? Okay. What I want to do is write it as a power series instead. So realize that you can rewrite this like this. Now, why would you ever want to rewrite it like this? We could argue. You wouldn't. How should we do this? 1 minus... that. Do you agree that's the same thing? Right? You square the x, then you make it negative, then you subtract it. If you did that, you get this, wouldn't you? Yeah? And so now, coming back up here and looking at this geometric series and looking at the right side here, this x right here, we have the format of 1 over 1 minus some yellow, right? Here, we have the same thing, 1 over 1 minus some yellow. And the yellow we have is, instead of just being x, it's negative x squared, isn't it? And since this looks exactly like this, but switching x to negative x squared, I should be able to write it like this. As long as I guarantee that the yellow part, the absolute value, was less than 1, right? So I'm going to write down next to this that this is equal to 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus dot, dot, dot. So replacing all of the x's in here with negative x squareds. And I'm going to put at the end of this, if what? As long as the absolute value of negative x squared is less than 1. So I'm just trying to get you to see, first of all, here, that you can rewrite this way. And if you can control that piece that you're putting in and make sure that the absolute value of it is less than 1, then you can rewrite it with this. And now what I'd like to do is rewrite it in the sigma notation. So what would this be in the sigma notation? I'm going to continue that. Equals down here, equals sum, n equals 0 to infinity of, just replace x with negative x squared, right? Negative x squared to the n. Yes? Which is also equal to negative 1 to the n times x squared to the n. Do you agree with that? Just looking at this negative in front of the negative 1, and then breaking this up into 2 factors, applying the n power to both. And then on this last one, I'm going to put x to the 2n instead of x to the x squared and then to the n. There we go. That is written as a power series. So what you always want to try and get at the end for a power series is you want to get the x part, this is the x minus a right here, to some power of n. And if it happens to be squared or cubed, you just put it up as a 2n or a 3n. But you want to peel off the constant. See, the negative 1 to the n is that c sub n that we had back when we first started talking about power series. Where is it? Whoa. Right? C sub n is some sequence that's changing, but x isn't part of it. And then we have the x minus the a and then to the power n. So that's why we were not okay with leaving it like this. We wanted to get that negative 1 off of the x. All right, that pretty straightforward? This right here can be represented as this, as long as the absolute value of negative x squared is less than 1. Isn't this the same as saying if the absolute value of x squared is less than 1? Because negative doesn't matter with the absolute value. And then if you square root both sides, you basically get this. And so your interval looks like this. This is your interval of convergence. And why don't I need endpoint checks? Because it's geometric, and we know what happens with geometric series. At the endpoints, right, it would diverge. Now you may again ask, why in the world would you want to do that, right? Because what I'm telling you is that if you want to plug a number into this to get an answer, you could also plug the number into this. You get the same answer. But this is very clean, right? Plug in 2, you get, what, 1/5? You're done? You plug in 2 here, then you'd have to actually sum it up forever, which would be impossible. So why would you want to do that? Well, that's not the point, okay? Just bear with me for a little while, because we would never want a power series for that because it's straightforward. You have the function. You have its value at any point. All right, another one. How about 5 over, I'll say f of x again. Three minus or plus 4x. And really, we're going to be focusing all of our attention on using this geometric series for these problems, at least for now. So I want to try and make it like this: 1 over 1 minus some junk, right? That's what I'm going to try and force to happen here. So the first thing I'm going to do is I'm going to just pull the 5 out of the whole thing. And the next thing I'm going to do is try and get that to be a 1 instead of a 3. So what? Factor out of 3. You factor 3 out of the bottom. It'd be like this, wouldn't it? 3 and then 1 plus what? 4/3 x. Yes? And that 3 can actually come out underneath the 5, so 5/3 times 1 over 1. How about I rewrite that as a minus negative 4/3 x. See how I'm just like playing this game of trying to make it look like 1 over 1 minus something? And so here's my junk. That was like what the x was in the geometric series, right? So according to the formula, this should be equal to a constant, 5/3 I'm going to pull out in front, times, let's rewrite that as the series, sum n equals 0 to infinity, and then what? Negative 4/3 x to the nth power. If what, though? This is only true if what? The absolute value of negative 4/3 x is less than 1. So as long as that's true, that's a power series representation. But we can't leave it like that because we got that negative 4/3 in front of the x, all of it to the n. So why don't we split that up, right? 5/3 sum n equals 0 to infinity. How about we put negative 4/3 to the n and then x to the n? Is that all right with you? That's the same thing, right? I've separated my x from the constant that keeps changing in front. So this piece right here is like my c sub n. This is my x minus a to the n. You'll see it? And then this out here is just some constant that's just going to multiply times that at the very end. So that is our power series representation. Let's make sure, though, we have a control on that absolute value. So let's get our interval of convergence. So from this, that's really 4/3 times absolute value of x less than 1. So the absolute value of negative 4/3 is just 4/3. And the absolute value of x is the absolute value of x. Multiply by the reciprocal, 3/4. So what's my interval of convergence? Negative 3/4 to 3/4. And do not include endpoints because we're using a geometric series, so we don't have to check it. This all right? One more of these. Does this seem straightforward or not? I mean, as long as you can massage it to make it look the way you want. Same instructions. Rewrite this as a power series. Uh-oh. That x cubed seems like it might be posing a little bit of an issue here on top. But no fear, this is just going to, let's just pull that out. See if you agree with that first. X cubed is being multiplied, so it's just pull it out front. That's the same as having it up here. I don't like the 4 here, so I factor out a 4, which leaves me with a 1 plus 5/4 x to the 7th. And then I'm going to pull the 4 underneath the x cubed, and I'm going to change the plus to a minus minus. I'll actually put 1/4 x cubed instead of x cubed over 4. 1 over 1 minus negative 5/4 x to the 7th. That should do it. That should be the thing, the piece right there. I've got the 1 over 1 minus junk. So that should be equal to 1/4 x cubed times a sum, an infinite sum. So notice the 1/4 x cubed just comes out, right? It's okay to leave it out here, and the reason why is because n only if the index is only affecting n, and this doesn't have an n in it, so I don't have to worry about it. And then here, this will reduce down to negative 5/4 x to the 7th to the nth power. We don't like that negative 5/4 attached to the x, so I'm going to peel it off. So I'm going to go negative 5/4 to the n, then x to the 7th to the n, and then what? Where did my x cubed go? I'm going to put it back in. Right? That would be okay to put the x cubed back in. This is 1/4 sum n equals 0 to infinity, negative 5/4 to the n, x to what power? 7n plus 3. Good. So x to the 7th to the n is x to the 7n, but x to the 7n times x to the 3rd, you add the exponent. 7n plus 3 is 7n plus 3. That's it. That's your power series. How about your interval of convergence? This is all true only if the absolute value of negative 5/4 x to the 7th is less than 1, right? That's the only way this will be true. So take your absolute value of negative 5/4, which is 5/4, multiply both sides by the reciprocal. So you get the absolute value of x to the 7th is less than, what, 4/5? And how can you get rid of the 7th power? 7th root. The absolute value of x must be less than the 7th root of 4/5. And so your interval is going to be positive that and negative that. Don't include the endpoints. So interval convergence is here. The answer is here. All right, up to this point, I would hope you sitting there are going, why in the world would I want to take something that's pretty easy to look at, right? And pretty easy to evaluate, plug a number into that. Why would I ever want to change that into something so complicated? An infinite sum, right? I mean, it just doesn't seem natural that you would want to do it. I told you there's a reason why, so we're building up to it, all right? We're not there yet. But we need some new stuff before we can get to the good stuff. This is what's called term by term differentiation and integration of power series. So we remember that in a Cal 1 class that if you have two functions, f plus g, and it didn't matter if there was addition or subtraction, and you take the derivative, that you just split it up. You do the derivative of each one. And if there were 3 of them, you just split it up into 3, 4, 5, 6, didn't matter how many, right? So differentiating two functions being added together is very easy. Also, integration worked the same way. If you want to take the integral of f plus g, you integrate each one separately, right? Yes? So what I'm saying, or what this is saying, is that if for some reason you have a function and you just happen to want to convert it to its power series, then if you wish to differentiate that function now, instead of differentiating the original function, you can differentiate the power series term by term. Now there's infinitely many terms, but the further you go, the closer you get to the true derivative. And integration the same way. And what this is kind of leading us to is the fact that if you were to reach your hand into the bag of functions and try and integrate something, odds are you're not going to be able to. I mean, we went through all the techniques of integration, integration by parts and partial fraction decomposition, trig sub, all these different things. We realized how difficult it was to integrate. This is saying that as long as you can turn it into its power series, you can integrate and differentiate term by term, which should be easy because all power series are power functions, right? Powers of x. Do we all know how to integrate and differentiate x squared, x to the 7th? I mean, we can all differentiate powers of x easily. There's a simple algorithm for it, right? So if we can somehow turn a function that might be very complicated into its power series, then integration and differentiation should be an exercise in power rule. That's all it should be. And this is where Newton's calculus was so much better than Leibniz, because those are the two fathers of calculus. Newton is the one who used the power series. Leibniz didn't have power series. So there were functions that Leibniz could not integrate or differentiate that Newton could. And this is what he used. So very powerful implications here. And this is exactly the way your computer does it. If you ask your computer to integrate something or differentiate, it does not sit there and do trig sub. It doesn't think like that, right? It converts to power series, then it runs an algorithm for finding derivatives or integrals, and then computes. It's all multiplication, addition, subtraction, right? 4 different operations. It's all your computer can do. So very, very powerful. All right, so let's see how it works. This is a theorem. Right. If f of x, well, hold on. If a power series this is our standard notation for a power series. So if a power series has a radius of convergence r, which is greater than 0. So let's just talk about what that's saying for the theorem. This is the condition you need for the theorem to work. You have to have a power series that has a radius of convergence that's bigger than 0. Tell me what that means. It can't be a point, right? So that means your radius of convergence is either what? Everything or an interval, right? So as long as our power series has it's defined, it converges on some interval or the entire number line, then here's the result. Then we can write f of x to be equal to the power series and it is well defined. On its interval of convergence. I.e., its domain. All right? So what we're doing is we're saying, We have a power series. It's got an interval of convergence that's more than just a point. Therefore, I'm going to define this to be a function, and its interval of convergence is what I'm going to be calling its domain. All right? So we've got this. Further, this function which is equal to c sub 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus dot, 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 right? That's what it is if we write it out, correct? So we can write out the power series just by expanding it out. And one, there's going to be two things here. One, the derivative of this function should be equal to what? Let's see. We're going to do it first by looking at this. What is the derivative of this? C sub 0. It's a constant, right? What's the derivative of a constant? 0. I'm going to put 0 here even though we don't need it. Plus, all right, what's the derivative of this? So C1 is a constant, right? So we'll just bring it with us. What's derivative of x minus a with respect to x? Just 1, right? Just 1? So C1. Plus, okay, now the next one. We have C2, which is a constant. We have to take derivative of x minus a squared. So chain rule, right? 2 comes out, power comes down. The 2 is going to hit the C sub 2. So it's going to be 2 C sub 2 x minus a to what power? First power. Times the derivative of x, which would be 1, right? Plus, next one. C sub 3 is a constant. We'll keep it. What comes out? 3 comes out. 3 C sub 3 x minus a what? Squared. Plus, do you want to do another one or you get the idea? Get the idea? I would like for you to now write this as a power series. So tell me what's happening. Let's look at the C's. I start out with what? C sub 1, C sub 2, C sub 3, right? So it's like just going up C1, C2, C3, C4. What about the number in front of C, the C? 1 C1, right? 2 C2, 3 C3, 4 C4. So the number in front should always be the same as the subscript on the C, right? So N. And then what about the power on the x minus a? Here it's 1, here it's 2, here it's 0, isn't it? So it's 1 less than the n? So tell me if you believe this. Would this work? N equals 1 to infinity. What did we say came out? There was an n, right? C sub n x minus a to the n minus 1, right? That would create that series? Yes? But look everyone. Isn't that just the power rule on this? Look at this. If I said take the derivative of this, what would you do? N would come out, right? And then you reduce the power by 1, wouldn't you? But there's one little subtle thing. What changed? The starting point. And you have to remember that for differentiation. When you take a derivative of a power series, if it started at 0, the derivative is as simple as pulling the power down and doing regular power rule, but you must shift this index, right? Index changes to n equals 1 instead of n equals 0. What would be wrong if you forgot that? What would you get? Would it matter? What would, if I plug 0, like if I forgot and just put 0 here, I would get what? 0, which would kill everything off. C sub 0, is C sub 0 defined? Yes, because the original function, we started at 0, right? So C sub 0 would be defined. But look at this part right here. 0 minus 1 would be negative 1, wouldn't it? Yes? So it would be this on the bottom. Do you agree? So technically, this right here would kill it off, yes? Because it would be 0. But it's a danger point later if you forget that shift, because we're going to be putting two power series together. And if they don't have the same indexes on starting points, you can't just paste them together. So remember the shift, even though it doesn't get us into a big trouble here, it will get us into big trouble potentially later. All right? All right, so that's how the differentiation works. How about integration? So this will be 2. What would the antiderivative of f of x be? And we put dx because it's with respect to x. So let's go back up to f, and let's integrate this guy right here. What's the antiderivative of c naught? C naught x, right? C naught x? Agreed? So can I do this? You know what? Before I put c naught x, can I put this? Do we know that with every antiderivative we're going to have plus c at the end? I'm going to put it in the beginning. The next one will be, you said c naught x, right? Yes? Is it all right if I put x minus a? Does that change anything? So let's just look at it real quick. C naught times x is c naught x. Got that. What's c naught times negative a? It's a constant. So, we put it together with this. It's still a constant. We don't know what it is, right? But I'm doing that so that we can maintain the pattern of everything that's going to come. What would the next one be? What's the antiderivative of, where are we? Right here? So C1 is going to be here, right? What's the antiderivative of x minus a? X minus a squared, but then over 2, right? So it'll look like this. C2 over 2 x minus a squared. Sorry, C1, thank you. C1 over 2. And then we're going to start to pick up a pattern here. What's the next one going to be? C2 over 3 x minus a cubed. Plus, now dot, dot, dot. The next one would be C3 over 4, x minus a to the 4th, and so on and so forth. Can we rewrite this as a series? So the constant out here, right? The plus c, this right here, I'm just going to put it right here. C plus, and then a series for the rest of it. What do you think? Started at 0. C sub n over what? N plus 1. N plus 1. Because isn't the number below each of the c's 1 more than the index? Right? So if we plug in 0, we get c sub 0 over what? 1. Okay, that would work. And then x minus a to the n plus 1. So plug 0 in. Let's just check that. This c is already accounted for. It's right here. Let's just check by plugging in 0, we get this first one. Yes? Does it work? Plug in 2, do we get this? Or plug in, sorry, 1's next. Do we get this? Yes? And this, and this. And so it works. Now, again, though, do you remember the power rule? I mean, just go right here and do the power rule. This is a constant. What's the antiderivative of x to the n power? 1 over n plus 1, x to the n plus 1, isn't it? So this is, again, this is just the power rule happening on our original sequence that was inside the series. And look, the index doesn't change for integration. It still starts at 0. All right. Y'all doing okay? Half an hour. I know. I told you it's a marathon today. Here's an example. Write as a power series. That star just means you should really understand what happens in this example. Because this is tricky. I think what we've done up to this point, especially the examples that we did just a little while ago, we were trying to get all of them to look like, we were trying to get them all to look like this. That's what we were trying to do. Make it look like this so we could convert it. The problem with this is that squared that's on the outside. You cannot resolve that squared on the outside. You can't just say, oh, I'm just going to take that series and square it. Think about that. If you were to try and say, oh, look, this is 1 over 1 minus x times 1 over 1 minus x, right? Do you agree that's true? Don't write this down, but do you agree that? And then you say, oh, that's sum x to the n. That's sum x to the n also, isn't it? N equals 0 to infinity. The problem is, how do you multiply two infinite series together? Is this equal to sum x to the n times x to the n? Is it or not? In other words, is that x to the 2n? Because isn't that what that means? What do you think? Just try it. Just try it. Just see if it works. Just start at n equals 0. What is this? N equals 0, you get 1. N equals 1. N equals 2. 3. Okay? That's what this is, right? Now, come back up here. What's this one right here? What's just this one? 1 plus x squared plus forever, right? Times this one, 1 plus x squared forever, right? And if you multiply these together, what's the first number you get? 1 times 1, 1. The next one you get, 1 times x, x. I see no x's. You see? 1 times x squared, x squared. 1 times x cubed, you have a cubic term, right? I see no cubes. This does not work this way. Now, if you add two series together, you can put them together, but when it comes to multiplication, it does not work out as clean, unfortunately. Now, we actually do have a way of doing this. It'll be later on, but for now, that's no go, all right? No go. So where does this differentiation whole thing come into play? I just realized something. 1 over 1 minus x quantity squared is actually the derivative of this, isn't it? Do you agree with that? Remember, this right here is the same as 1 minus x to the negative 1, isn't it? Isn't that what that is? And if I say take the derivative of it, the negative 1 would come out. You do this to the negative 2. Then chain rule, you'd multiply by the inside derivative, which would be negative 1. That would hit the negative 1 that came out, and you'd have a positive 1 over 1 minus x squared. Yes? Okay. So I just happened to realize that this is the derivative of that. Yes? And is this something you know? Yes, that's what we were trying to get earlier, right? So watch what I do. Okay, so that's equal to the derivative with respect to x of this power series. That's directly changing this to this, right? This goes to this. And also keeping in mind the absolute value of x must be less than 1 for that to be true, right? So you mean to tell me that this right here is just the derivative of a power series? Yes? And what's the derivative of a power series? We just said that you look at the inside and you use the power rule, right? But because we're doing a derivative, we have to remember to shift the index over 1. So take the derivative, so I'll turn to green because we're taking derivative. And the derivative notation goes away, and this becomes what? Sum n equals 1 to infinity. Now the power rule, n comes out, x to the n minus 1. Okay? That's it. That's the power series for that. Make sure it looks like it's in the right form so I can be done. C sub n. This is like my x minus a to the n. I realize it's n minus 1, but it's okay. As long as this is a linear expression, we're okay. As long as that doesn't say like n squared minus 1, then it's a power series. Now, we also like to sometimes write out a few of these so we can kind of see what's happening. If n is 1, what do you get? 1. If n is 2, what do you get? 2x. N is 3, 3x squared plus ... Next one would be 4x cubed, 5x to the 4th. Keep going. As long as what? Absolute value of x was less than 1, this is good. So let me try and illustrate something real quick for you, all right? This is just a quick illustration. Let's say I wanted to do an integral from one half to 3/4. All right, from 1/2 to 3/4 of 1 over 1 minus x squared dx. I could find the antiderivative of that very easily, all right, because I kind of needed that up here, didn't I? I had to realize that that was a derivative of something. But let's just say I'm going to not try and get that antiderivative. I actually know that this right here, written as a power series, is this, isn't it? So what I could do is instead integrate from from 1/2 to 3/4. I could integrate 1 plus 2x plus 3x squared plus ... forever dx. Wouldn't that be the same thing? As long as the x was what? Between -1 and 1, which in this case, I'm integrating over that interval. And now just do the antiderivative of each one of these. So x plus what? Squared plus x cubed. Boy, these are working out great, aren't they? Plus x to the 4th, evaluated 1/2 to 3/4. So then I just plug in, oh, this is plus dot, dot, dot. So I plug in 3/4, I plug in 1/2, I subtract the 2. And I would have an approximate answer, wouldn't I? The further I go out, the better my answer is. So I'm showing you an alternate way of doing integrals, but it relies on the fact that you can come up with a power series for these. So you might be saying to yourself or thinking to me like, well, my functions over here have to look pretty damn good, right? In order for me to do this, because I've got to be able to use this formula, right? I've got to be able to make it look like 1/1 minus x, or else I'm stuck, right? Or else I have no business, I can't do anything with it. Well, that's where the next section, we're not going to start today, I don't think, no. That's where the next section comes into play, which is a formula to find the power series. Instead of relying on trying to match it up to something we know, it's a formula, a generic formula for finding the power series for any function. And that's the big thing that Newton got, right? Example. Express as a power series. F of x equals natural log of x plus 5. Here's the power series that we're trying to. I don't have the graph on here. Oh, here it is. Let me zoom out a little bit. Oh no. Oh no. All right, forget it. I'll come back to that. All right, so look, all we have right now is what's on the board over there. If we can somehow make that look like 1/1 minus x, then we can convert it using that geometric series expansion. Natural log of x plus 5 is nowhere near 1/1 minus x. However, what? The natural log of x plus 5 is actually the integral, the antiderivative, right? This is the antiderivative of something that does look like that. What is the antiderivative of? 1/x plus 5 dx. Do you agree? Yeah? And because of that, I know that I can rewrite 1/x plus 5. Let me do that on the side here. 1/x plus 5 can be rewritten as 1/5 plus x, but that can be rewritten as 1/5 times 1/1 minus -1/5 x. Shit, okay. So we did all these just a little while ago. If you have this, I'll switch it over. I need that 5 to be a 1, so I factor a 5 out. Here's the 5 I factored out on the bottom. It comes out as a 1/5. I need the plus to be a minus, so a minus minus. Yes? Yeah? So that's all my little scratch work. And now I can rewrite this as 1/5, and then what is that as a series? Sum n equals 0 to infinity of negative 1/5 x to the n. How about I write this? That all right? Because we know we're going to have to split off the negative 1/5 to the n, split that off from the x to the n. Questions? So I can replace this right here with that. So what should I do with that 1/5? Pull it out. Pull it out of the whole integral. And then I have in here a series, infinite series. And I have negative 1/5 to the n, x to the n, and then all of this dx. So I want to integrate this. And be careful, because what is this right here? This is our c sub n, isn't it? Our c sub n. And this part right here, this is our x minus a to the n. And the reason I want you to be careful with that is because when you go back and you look at the formula for integration, if you have an original power series, your c sub n is separated from your x minus a to the n. When you actually do the antiderivative, does that c sub n formula change? No. All you're doing is going to put an n plus 1 underneath it and an n plus 1 on the power on the x term. That's it. You don't mess with the power on the c sub n is what I'm getting at. So this should be equal to, here's my 1/5, and then no more integral sign, because I'm actually taking the antiderivative of a power series. I should have sum, do I change this index? No, not for integration. N equals 0 to infinity. Negative 1/5 to the n over n plus 1 x to the n plus 1 plus some constant. And this is where, again, I said it's good practice to maybe write a few of these out. 1/5. Let's let n be 0. What happens if n is 0? That's 1, and then that's 1, and then that's x. Yeah? So you just get 1/5 x plus, now what do we get if we let n be 1? Negative 1/5 over 2, so negative 1/10, yes, negative 1/10, and then x to the second, but then we have times 1/5. So what? Maybe change this to a minus? Minus what? 1/50th x squared. Plus, what would the next one? We'll just do one more. If n is 2, what do we have? Square this. 1/25th, divide that by, and it's 2, so divide that by 3. 1/50th, oh no, 1/25th divided by 3 is 1/75th times 1/5. 5 times 75? 375. So 1 over 375 x to the, where are we, third? And then we keep going. Understand? Plus dot, 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 dot. Next one would be minus, but who cares? That is the power series expansion. Now, we didn't get the interval of convergence here, but we would need what? From this, absolute value of this to be less than 1, so multiplied by 5. So you need like the absolute value of x to be less than 5. And this would work. So believe it or not, on your calculator, when you type in the natural log function, it is not doing anything other than a power series. It is doing an expansion. So let me get you to do this. Let's let x be 4. I just want to show you how this works. If x is 4, what is natural log of 4 plus 5? So someone on their calculator do natural log of 9. Tell me what it is approximately. 2.197. Okay, now what I want you to do is replace this with 4. So on your calculator, do what? 4 times 1/5 is 4/5 minus 16 over 50 plus 64 over 375. And just do those first three and tell me what you get. What? That's it? 0.651? We're going to have to go further out? Well, let me see if I have this animation here. See, this thing is still not responding. Okay, close the program because I'm not happy with it. So watch, I'm going to go to Wolfram Alpha and I'm going to type in log. Wolfram Alpha treats log as natural log, okay? X plus 5. I'm going to hit enter. That's all I'm going to do. And I'm sure if you use Wolfram Alpha before, you say, it throws all this information out and you're like, what is all this? I just want to know what log of x plus 5 is. It does a lot to that expression. So come on. Where'd it go? And why is this thing running so slow? I don't want pro support. Series expansion at x equals 0, which is what we had because, well, we had it at 5 actually, -5, didn't we? If you look at that, well, no, we're going to address this next time. Look at our series. We had 1/5 x minus what? 1/50 x squared and then 375. So we've got that. But didn't we have plus c? Plus c? That's the constant out there, log 5. So that's why we're off. If you add log 5 to that, you would get it. We need to get into this more. What I more wanted you to see is that Wolfram Alpha will give you a series expansion. All right, 5 minutes. All right, go away. Man, we still got a ways to go in here. So I printed out the notes for the rest of the term. And it looks like we're about halfway through what we need to get to. We have, what, 2 full classes? So I think if we keep this pace up, we might be able to hit some of the stuff that we're supposed to hit, like parametric and polar coordinates, which will be good. I think this is a good place to stop, though. I don't think you have enough to really do any good damage to the section here, this section, but I'll put the homework up now in case you want to work ahead. But just be aware that you may run into issues. 3 through 11 odds, 15, 17, 19. So that'll be the homework for this section when I'm done with it, which will be next class. Make sure you do the homework for the previous sections that I put up. Y'all have a good day. See you Thursday.